Welcome back, everyone. Now, in the previous video, we introduced methods for solving non-homogeneous equations. And if you recall, what was required of us was that we had to sort of guess what the function should look like. And in particular, we had to guess in such a way that we had this self-replicating property that we could always sort of get this closure. When you take derivatives, you get the same kinds of functions back. Again, think sines and cosines, exponential functions, polynomials. Now, of course, that only works when the right-hand side of your differential equation is something that has this replicating property. But what if I gave you this? What if I said, go ahead and try and solve this differential equation instead? Cosecant of t. Now, cosecant of t is not a simple function. It's still trigonometric, but it doesn't have this derivative property where I take a couple derivatives and I get the function back, right? This is 1 over sine, and when I take derivatives of that, I get all kinds of mixes of sines and cosines and tangent functions and issues. So it's not clear to me that I should be able to try a specific solution that is, some linear combination of trigonometric function. So there's got to be a better way, right? And there certainly is. This is known as the method of the variation of parameters. So I'm going to step through with this example, and then we'll show the general method at the end here. But let's start with this. Okay, well, the homogeneous solution. Remember from the theorem, or the theorems that I had on the previous board, or previous video, the homogeneous solution is an integral part, right? It's the easy part that we can get sort of with minimal effort from these things, and it's the first piece of finding the solution to the differential equation. So in my case, I get r squared plus 4 for a characteristic equation. That thing has roots plus or minus 2i. We have already handled the case of complex conjugate roots. So in this case, I get yh of t is c1 cos of 2t plus c2 sine of 2t. Okay, so I got the homogeneous equation, or the homogeneous solution. Question is, what can I do with it? Well, if you think back to what we did with the method of reduction of order, we said that if I know one solution to the homogeneous equation, then I can leverage it to find the other one with the reduction of order method. We're going to kind of do the same type of idea here. We're going to say, I know the solution to the homogeneous equation. Let's leverage it to try and find the solution to the non-homogeneous equation. And the way that we're going to do this is we're going to let c1 and c2 be functions of t. So this is y of t is u1 of t cos of 2t plus u2 of t sine of 2t. Okay, so I am taking the homogeneous equation and I'm letting the constants vary as functions of time as well. Now, that's where the name of this method comes from, variation of parameters. In this case, the system parameters are c1 and c2. You have some freedom to choose those things. Sometimes people call this method variation of constants as well. Again, c1 and c2, but they're allowed to vary with time. That's where the variation part comes from. Okay, let's run with this for a moment. Let's take a derivative. Y prime of t. This is going to give me u1 prime cos of 2t plus, minus u1, 2u1, sine of 2t plus u2 prime sine of 2t, and then plus 2u2 cos of 2t. So all I did was took a derivative here. Now you can see things are starting to get a little hairy. They're getting a little ugly. But what we're going to do is we will require, now it turns out that this is necessary for the method to work. We need an assumption on u1 and u2. In this case, our assumption that we'll make is that u1 prime times cos of 2t, that's this part right here, plus u2 prime times sine of 2t is equal to 0. That's this part right here. So that means that this piece drops out, and so does this piece. And I am left with no more derivatives in u1 and u2. Now, this is a technical condition that we're not going to go too much into why it's here, but I do want to point out one thing. First of all, I have two unknowns at the moment, u1 and u2, but I'm only going to have one differential equation to put them in. That's not enough to solve for both u1 and u2. So the question is, what do? Well, I need another equation. In this case, I've got an equation that involves u1 prime and u2 prime that will allow me to pin down exact u1 and u2s. Okay, with that in mind, now I get the second derivative of u. Remember, this piece and this piece drop out by my assumption here. And now I get, so I get taking this derivative minus 2 u1 prime sine of 2t minus 4 u1 cos of 2t. That's just the derivative of this product. And then same thing over here, plus 2 u2 prime cos of 2t. And then minus 4 u2 sine of 2t. Okay, so it looks like it's going to be a pain, but I've got y double prime, I've got y, I can put them into the differential equation. So let's go ahead and do that. Let's say put into the differential equation, right? One of the most common things that I write on this board in front of me. Well, in this case, you can see, in fact, I have minus 4 u1 cos of 2t, and I'm going to have plus 4 u1 cos of 2t. So they're going to cancel. Same thing, I have minus 4 u2 of sine t, and I'm going to get plus 4 u2 of sine t. So they're going to cancel. That means that all I'm left with in the differential equation is minus 2 u1 prime sine of 2t, and then plus 2 u2 prime, move that over a little bit, cos of 2t, and it's still equal to cosecant of t. That's pretty nice, right? Things cleaned up very, very nicely for me, and that's coming a lot from the fact that this is the homogeneous solution, right? These cos of 2t and sine of 2t, and with u1 and u2 being arbitrary here, that is the same as just multiplying through this equation by u1 or u2. So you still get it equal to 0, and so everything is dropping out. And this is very, very similar to what we did with the reduction of order method. We saw something similar happen when we had this dropping out of terms. And even more similar to reduction of order, I only have a first derivative in u1 and a first derivative in u2. So I took a second order differential equation, and now I'm reduced to a first order differential equation. So it's not too bad, right? I dropped down in order. This is very, very intimately related to the method of reduction of order. Now, let's keep going. From this thing right here, I can rearrange that to get u1, right? So from star, so I'm just using this notation star so that I don't have to rewrite it. Star means this equation right here, my restriction, my requirement. Well, that gives me u2 prime is equal to minus u1 prime times cos of 2t divided by sine of 2t. Okay, it feels like something is coming together maybe, because now I've got u2 prime. I can put it in here. And so let's see what happens. This gives me u1 prime is equal to minus 3 cosecant of t. So I'm going to collect the u1s after putting this in here. Let's collect them all up, put them on the left-hand side. So I'm going to skip a couple steps here, and I want you maybe to pause the video and see if you can, do exactly what I'm doing with this. So if you can make it simplify in exactly the same way. Okay, so now what I'm getting is minus 3 cosecant of t times 2 sine of t, or sine of 2t. Okay, now I just need to do straight integration. So the question is, how do I integrate this? There are many, many different ways that you can integrate it. You can use a computer-assisted software, something like Wolfram Alpha. That's fine. But let's go ahead and let's actually just do it by hand. And the way that we have to do this is using the double angle formula. So in this case, we can represent sine of 2t equal to 2 of sine of t times cosine of t. So that's the double angle formula. This gives minus 3 cosecant of t, and then sine of t times cos of t. So again, that's the double angle trigonometric identity. And the beauty of this is that cosecant is 1 over sine. So I have 1 over sine times sine. They disappear. And now I'm left with u1 prime is equal to minus 3 cos of t. Nice, easy integration. This gives me u1 of t is equal to minus 3 sine of t plus c1. And the plus c1 acting just like it did with the reduction of order method, right? The only thing here is this is going to give you your homogeneous solution back, right? Because remember, the general form of my equation was u1 times the homogeneous piece plus u2 times the homogeneous piece. So the c1 here is going to make sure that I get a c1 times y1, right? My homogeneous part of my solution. Whereas the minus 3 sine of t, well, that thing is going to give me the particular or the specific part of my solution. Now, look at what I have. I have u1. I also have u1 prime, which is equal to minus 3 cos of t. So that means that I can get u2. So I get u2 prime is equal to, in this case, I'm going to get 3 cos of t. That is just u1 prime with the minus out front. And then cos of 2t divided by sine of 2t. Okay, so it's a pretty ugly integration, but nonetheless, it can be done. Go ahead, see if you can work it out. You can use a ton of double angle formulas. Still not going to be the nicest thing that you've worked with ever, especially in this class, but you're going to get, in this case, if you just do the integration, let's take a look at it. You get 3/2 the natural logarithm of the absolute value of cosecant of t, and then minus cotangent of t. So a very, very ugly logarithmic term here, plus 3 cos of t, and then plus c2. And what all of that means is you can take it all and you can put it back into the differential equation. So let's do this. And so therefore, your solution to your differential equation, let's put the homogeneous part first. It's coming from the c1 and the c2s here. So this is c1 and then cos of 2t plus c2 sine of 2t. And then we have the rest of this. So minus 3 cos of t. And that was part of u1. So, sorry, that's a sine, not a cos, pardon me. And that's being multiplied into cos of 2t. And then all of this big ugly thing, plus 3/2 the natural logarithm of cosecant of t minus cotangent of t. They're just functions, right? They're ugly, but that's okay. They're just functions. First of all, this thing is multiplied by sine of 2t. And then the last term out here, plus 3 cos of t sine of 2t. And that gives us our solution to the differential equation. So that is what's called the method of variation of parameters. Now, let me give you the general theory here. It works exactly the same way, but let's spell it out on the board so that we have nice formulas that we can use as we go through this. So generally, so we can say if we're given a differential equation, so given, and in fact this works for any first order linear or second order linear equation equal to some inhomogeneous term, so say G, we can let YH of t equal to C1 Y1 of t plus C2 Y2 of t, where in this case, so this thing will be the homogeneous solution. And Y1 and Y2 are a fundamental set of solutions for that homogeneous equation. Then, following exactly what we did, so homogeneous part, then we can set y of t equal to u1 of t and then y1 of t plus u2 of t, y2 of t. And I'm going to emphasize this. You have exactly this condition again. So again, we require, maybe. Well, what do we require? We require that derivative condition. So u1 prime y1 plus u2 prime y2 is equal to 0. Two equations now. You're going to put this into the differential equation, and you're going to use that thing. And let's say going through all the steps, so going through the same steps as the example. So my example was that I took the derivatives, I used this condition, I put them into the differential equation, I again use the condition. Well, you can find a very, very simple form for u1 and u2. So the first thing is that the differential equation becomes this. So the differential equation will become u1 prime y1 prime plus u2 prime y2 prime is equal to g. This is what happens when you put all of this into the differential equation. Again, you're going to have to use the fact that y1 and y2 are solutions to the homogeneous equation in the same way that we saw this term drop out when we put it into the differential equation. That came from the fact that cos of 2t was the homogeneous solution. Same thing with this term right here, which again came from the fact that sine of 2t is part of the homogeneous solution. So again, u1 prime, y1 prime plus u2 prime, y2 prime. Go back and double check. That's exactly what we have here for our differential equation. u1 prime, y1 prime, u2 prime, y2 prime equal to g. Then you can use the requirement. So using star, we get, well, you can substitute for u1 or u1 prime or u2 prime. It's up to you. So for example, you can get u1 prime is equal to, so once you isolate for u2 prime, just like we did right here, so just replacing everything with respect of y1s and y2s. So again, I don't want to bog you down in the steps. I mostly just want you to know it's exactly the same as what we've already done. Well, in this case, you get g of t. That's the cosecant part that we already saw. And then that's going to be multiplied against y2 of t. And that will be divided by y1 of t times y2 prime of t minus y1 prime of t times y2 of t, which we've seen this before, right? That's exactly the Wronskian. So this is actually going to be g times y2 divided by the Wronskian of y1 and y2. So we have a nice little compact way of writing that because now we know what the Wronskian is. Well, similarly, we get a formula for u2 prime. So if you were to substitute instead for u1 here in terms of u2, then what you would get is you would get an equation here with just u2's in it. So basically just not doing this substitution, doing it the other way around. Then you can similarly find an equation for u2 prime, which is going to be g times y1 divided by the Wronskian. So very, very simple, right? All that's happening here is you multiply g by y2, divide by the Wronskian, and you get the derivative of your unknown u1. Then the hard part is just integrating. That's all that you have to do. Right? Now you can integrate to find u1 and u2, and that will just come from whatever the specifics of these equations are. The thing I really want to emphasize to you is that none of this relies on what P and Q are, right? P and Q are going to determine the homogeneous part of the solution. And that's sort of encoded in the background of everything here, right? Because the homogeneous solution, y1 and y2, are going to heavily depend on what P and Q are, but it's all going to be hidden from you. If you already know what the homogeneous solution is, then the only information you need is what the homogeneous solution is and whatever g is. Then it's easy, right? It's just a computation of the Wronskian and a little bit of integration. This is all something that we can handle. All you need to do once you have it in this form, integrate up. You've got u1 and u2, and from this piece right here, you've got yourself your solution to your differential equation. Again, this is called the method of variation of parameters. I want you to understand why again, but it comes from the fact that these C1 and C2s that are used to build up your homogeneous equation, these are the parameters in your solution. You're letting them vary in time. That's where you get the u1 and u2 from in both of these cases. Now, last thing, if you forget all of these formulas, that's fine. You can work it through using exactly the same logic that we did when we did the example, right? You just need to remember that it has this specific form, u1, y1 plus u2, y2, and you'll need to remember that you have this derivative condition. The beauty here is you get very, very simple differential equations, and it's just a straight integration process. Now, whether or not that integration is easy, it's a whole nother problem, but in principle, integration can be done, maybe with the help of a computer. And so we've got ourselves into an area where we can handle this. At least it's something feasible, right? Instead of just a completely confusing and perplexing and almost impossible looking differential equation.